Alright, hey, welcome back to part 2 of retro programming. I want to go over the instruction set architecture of the PDP 1170. This is sort of the gory details, and I am definitely assuming that you've done some assembly language programming before. You understand basic concepts like what the program counter is, the notion of an opcode and an operand, read, modify, write instructions, things like that. If you're not familiar with those, this is probably not the best introduction to those concepts, but if you've worked with assembly language, some machine language on any processor, that's probably plenty of background. I just want to get into sort of the specific parts of the PDP-11, and it's a wonderful processor. It does some things that are kind of unique among a lot of processors, some interesting design choices that were made. So the sort of gold standard documentation for this is the PDP 1170 processor handbook. This is about 50 years old, out of print as far as I know, but bitsavers.org, which if you don't know about it, you definitely want to check it out, has copies of lots of good documentation. I'll put a link to this particular PDF in the description. It's got everything you would need to know about the instruction set architecture, the behavior of the CPU, but it is close to 300 pages. But it's well organized, broken down into parts. I'm going to go through just sort of the very briefest perusal of the concepts in here. But if you want to dig deeper, that's definitely the way to do it. If you want a quick reference, I'll also put this link in there. Somebody has uploaded scans of one of the PDP-11 programming cards, and these are super useful. So if you click through on those, you can download them as an ODG file. You can download that, or see it as a PDF. The ODG, you can edit it with various Office type tools. The PDF, if you have Inkscape and such, you can work with those directly. But it's basically two sides of a programming card. The way this was uploaded was here's one side of the front, and here's the other side of the front, and so on. But anyway, once you have that, you can print it out in a nice expandable with pocket size synopsis, and like I say, this has pretty much everything that you're going to want when you're writing code for the PDP, whether it's assembly language or machine language. So I'm going to refer to that in here, and I've made just a larger version of it across a few pages so that it's easy to read. So main thing that you need to know are the addressing modes of the PDP-11. So once you understand the addressing modes, everything else kind of falls into place. Basic background, so it's a 16-bit processor, so your instructions are 16 bits or multiples of. Your basic word size is 16 bits. When you say add or move, you're dealing with 16-bit entities, so 2 bytes. It has 8 registers, so R0 through R7, but 2 of them are special. So register R6 is the stack pointer, and register R7 is the program counter, and that's an extremely powerful characteristic of the architecture. We'll see why in a minute. So 8 registers. There's multiple banks of registers. There's different versions of stack pointers you can use depending on the privilege level of the CPU, but basically we just think of it as having R0 through R5, so 6 general purpose registers plus a stack pointer and a program counter. The I/O devices are all memory mapped, so the if you're using 16-bit memory, your addresses basically go from all zeros to this, and we tend to work in octal. I normally don't like octal, but since I've been messing with the PDP, I've done more with octal than I have in my whole life. But it's very convenient because the way the instructions are set up and stuff. we have lots of things broken into groups of 3 bits. So this would, you know, be 16 ones, right? So top of the memory address space. But usually there's a memory management unit that takes some of these addresses and maps them to other spots in physical memory. The physical memory can be actually 22 bits. And part of the upper address space is used for mapping I/O devices. So there's a unibus and there's a mass bus and some other things, and some of these addresses will actually be registers on you know, what would be physical devices. We'll deal with that in another video when we talk about working with paper tape punch and reader, floppy disk controller, things like that. And we'll just have certain registers we talk to interact with these devices. But mostly we just think of it as, you know, a 16-bit address bus, and so addresses from 0 through 65,535. Alright, so let's look at addressing modes. And one of the really nice things about the PDP is it's an orthogonal instruction set. So a lot of the instructions, for example, these double operand instructions, they have an opcode, which is 4 bits, and then they have 6 bits specifying a source, 6 bits specifying a destination. And so the move instruction, I can move from any operand to any other operand with those operands specified any way that I like. And so there's several addressing modes possible, and there's, you know, several different registers I can use with those addressing modes. So we basically have a set of opcodes, and then we have a set of addressing modes, and then we have a set of registers. And those 3 dimensions of our instruction space are more or less independent of each other. Alright, so this will make more sense as we look at some specifics. So let's just look at addressing modes. 8 addressing modes: register, register deferred, auto increment deferred, auto decrement, decrement deferred, index, and index deferred. Okay, what do these mean? Register is just straightforward. Just use the value of a register, either read it or write it. So if I use mode 0 and I say R4, it's just, you know, using the value of R4. Register deferred says I don't want to use R4, I want to take R4 as an address and use that address, the thing at that address, as the operand. We can also increment the register after we use it, or we can decrement the register before we use it. There's also a deferred auto increment, so this basically says I don't want to use R4. I don't want to use the thing that R4 is pointing to. I want to take the thing R4 is pointing to and use that as the address of the operand. So it's like a double level of indirection. Same thing with the auto decrement deferred. And then the index says, okay, following the opcode there's going to be another word, 16 bits, which we are going to add to the contents of the register. That's going to give me the address that I'm interested in. So we can basically specify a base address and then use the contents of the register as an offset from that base. Or we can do that with one level of deferring, and we can say, okay, take a register, look at its contents, add this number X, that gives me an address in memory, go to that address, read the word, that's the address of the operand. So what does this look like? It's not something we need to do generally at the machine code level. The assembler will take care of this for us, but it's nice to understand how these things work so that we can make good use of the assembler. So I'm just looking at this top part right here. Don't look at the bottom part yet. So if I say, you know, increment R0, and, you know, if R0 equals 5, it's going to change to a 6. Alright, if I say increment parentheses R0, it's going to look at R0, it's going to see a 6. It's going to go into my memory, and at location 6, maybe I have the number 15. That's going to get incremented to a 16. So take R0, use that as an address, go into memory at that location, increment what's at that location. If I say increment R0 deferred, and let's say at location 16 I have the number 2. So it's going to take R0, that's a 6, going to go into location 6 and see a 16. It's going to take location 16 as my actual operand. So in this case, it's going to take that 2 and increment it to a 3. And then if we do a post increment, if I say increment R0 plus, R0 is a 6, so it's going to increment the contents of location 6, and then when it's done, it's going to increment R7. So that's useful if we have, like an index where we're marching through memory and such. The pre-decrements are exactly the same. The index, so if I say increment 20 R0, and let's say down here at location 37, I might get an odd address error if I do this. I don't know. Let's suppose this is 16. Okay, so increment 20 parentheses R0. So R0 has a value of let's say R0 has a value of 16. So if I say increment 20 R0, it's going to look at R0, that's a 16. It's going to add 20 to that and get 36. It's going to take whatever value is at location 36 and increment that. And if I do increment at 20 R0, it would do the same thing, except that after it takes R0, adds 20 to it to get 36, and it reads the 6. It doesn't increment that, it uses that as an address. So it would go to address 6 and increment this. Okay, so lots of options there for addressing, and in general, when we specify an operand like this, we use 3 bits to specify the mode, and then 3 bits to specify the register. So if I'm doing register direct on R0, I would code 0000000. If I want to do register deferred on R5, I would put a mode of 001, and then the register would be 5101. And all those combinations are valid. What's cool about this is this notion that register R7 is the program counter, and that gives us some special capabilities. So for example, if I do auto increment on register 7, so let's say I say I don't know, let's move R7 plus comma R0. Okay, so remember R7 is the program counter, so this really says move PC plus comma R0. And let's suppose this is followed by the number 1, 2, 3, 4, 5, 6 in memory. Okay, normally a move instruction is 1 word, so this would be the next instruction to execute. But here's what happens. It looks at R7, that's the program counter, and let's say this is, location 1000. This would be location 1002. The next instruction would be 1004. Okay, when the CPU fetches this instruction, program counter starts off at 1000. After the fetch, it automatically increments it by 2, so the program counter is 1002. So it's pointing to the next, what would be an instruction. Okay, this says, don't move R7's contents into R0. Use this as an address. Take the contents of 1002 and move that into R0. So R0 now is equal to 1, 2, 3, 4, 5, 6. And then after you've done that, increment R7. So this becomes 1004. So what just happened? We said move R7 plus R0, and we followed it by 1, 2, 3, 4, 5, 6. Well, this number is the thing that got moved into R0. That's an immediate addressing mode. And now the PC is 1004, so whatever comes down here will be the next instruction to get executed. So we don't have a separate addressing mode for immediate operands. We use the auto increment addressing mode with register 7. So if I tell the assembler something like move immediate 1, 2, 3, 4, 5, 6, comma R0, that's how it will get coded up. move R7 plus comma R0, and the next location in memory, the next word, would be this immediate value. And so there's 4 modes like this. If I want to move from a location into a register, I can do addressing mode 3, which is auto increment deferred. So if I say something like move at PC plus comma R0, and my next location in memory is 1, 2, 3, 4, 5, 6, what does this say? Take the program counter, which is now pointing to this, read what's at that location, but don't move that into R0. Use that as the address of what we want to move into R0. So somewhere in memory, I've got location 1, 2, 3, 4, 5, 6 with, you know, some value in there x. This is going to take the value of x, move it into R0, and then increment the program counter so that now we're pointing at the next instruction. So if I say move at 1, 2, 3, 4, 5, 6, comma R0, that says don't move this number into R0, move what's at that address into R0. So we can access a location in memory and have it move that contents into our register. And this, you know, works with moves or increments or any of these instructions that take one of these source or destination bits. And we can do this on the left side, we can do it on the right side, we can do it on both sides. It's completely orthogonal, so we can put these together in any way that we like. 2 other program modes, relative and relative deferred, and these work basically the same way, except they let us specify displacements relative to the program counter. So this can help with making relocatable code. Alright, so that's the business of addressing modes, and like I say, if you understand the addressing modes, that's pretty much key to knowing the different ways we can interact with the CPU. There's also a processor status word. So you can see it right here, and it's got the usual bits you would expect for carry, overflow, 0, negative, and different instructions affect those codes. For example, if I say the clear carry instruction, it sets carry to 0, it doesn't affect any of these other bits. If I do, let's find another instruction. If I do a move instruction, it affects the negative and 0 bits, it clears the overflow, and it does not affect the carry. So if I want to see if something is equal to 0, I could do a move and then do a branch that tests that flag. And so for each instruction, you can see which bits in the processor status word are affected. So full list of opcodes and instructions available here. And they break out into a few different types. Single operand are things like clear, complement, increment, decrement, negate, test, and so on and so forth. And if you've done programming in other assembly languages, these kind of do what you would expect. These can work on words or bytes. So for the coding of them, there's 3 3-bit words that specify the opcode. There's 6 bits, 2 3-byte words that specify the destination register, which is also the source if you're going to like increment, for example, and 1 bit in the front, which can be a 0 or a 1 to indicate whether this is a byte or a word operation. And there's a table over here that square means 0 for word, 1 for byte. So for example, 1050 is a clear, 050 is a clear byte, and so on. So those are single operand. There's double operands, move, compare, add, subtract, Boolean operations, bit test, clear, and set, multiply, divide, arithmetic shift, XOR, and so on. There's a number of branch locations, and branches tend to use the program counter. So the new PC is the current PC after you've added 2 or more for fetching, plus 2 times an offset. This is the usual trick. Addresses are even for instructions, so if you want to jump a distance of 20, we don't want to actually store 20 in the instruction. We store half of that, 10, because we know the least significant bit is always a 0. So unconditional branch, conditional branches, and these all you just use displacement. So 1, 2, 3, 4, 5, 6, 7 bits of displacement, and then a base code, and this bit 7 is a 4 or 0 as specified in here. So you can go plus or minus 377 octal. And a bunch of conditional branches that all depend on the condition codes in the processor status word. And you can see the different conditions that apply for each of these. What else do we have? Jump lets you specify a jump destination using the standard 6-bit operand specification of a mode and a register. Jump to a subroutine and return from a subroutine. These need a register, typically the program counter, and then a specification of where you want to jump to. Mark is used as a convenience when you call a subroutine and you want to store a bunch of information, have local variables, parameters, things like that. You monkey around with a stack. Mark helps you do that. Traps and interrupts. So you know, interrupts are a whole separate topic outside what I want to talk about here. But basically, when an interrupt occurs, something happens to the processor. It pauses what it's doing, preserves some information about its state, and then goes somewhere else. So where it goes to, we call it vectoring, and basically depending on who caused the interrupt, it will look in a certain location for a vector, and that vector will tell it where to jump to, and also what value to load in the processor status word. So the other parts of the PSW, there's a 3-bit priority level, which controls the interrupt priority levels. So if you're at priority level 0, anything that wants an interrupt will be able to interrupt you. If you're at a 7, I believe nothing will interrupt you. So it's what the priority of the CPU is right now. Usually it's about a 5 or a 4. And then there's 3 different modes the processor can operate in. User mode, which is just, you know, everyday use. Supervisor mode, which is an elevated privilege. And kernel mode, which is a higher privilege. That's the level where the system is doing system level things. And there's a current mode, 2 bits, and a previous mode, 2 bits, and a bit to indicate which register set we want to use. What else? Traps and interrupts. So like I say, these cause the processor to go to a different location and potentially change its priority level, change its current mode, and so on and so forth. The other thing I want to mention is that peripheral devices, like I said, they're memory mapped, and we'll look at those in detail in another video. But there's some locations that correspond to not general memory, but to certain parts of the processor. For example, if I actually look at address 177.776, even though that says a 7 in the front, that'll actually refer to the processor status word. If I look at 177.570, if I read from that, it'll read the position of the front panel switches, and if I write to that, it will write to the LEDs. Now, doing this from the simulator interface does not always work, but doing it from a program will. We can also read and write the general purpose registers through certain locations from the console. So there's a lot of little fine-grained detail in there. And then on this programming card, there's also all the information about the different devices that are available. So if you want to work with the clock that's driven by the power line, right, its address is 777546. When it throws an interrupt, it will vector to location 100, and it has a priority of 6. There's a programmable clock which vectors at 104. And for these devices, we have different status and data registers that you can interact with, just like any other memory location. So the clocks are pretty simple. The line printer is pretty simple. Check the status, and if it's ready, you can send a character out to it. Some of these other devices, like the disk controllers, are a lot more complex. They have a lot of registers associated with them and so on. And there's tons of documentation that tells you all about that. This card also has some simple code routines for bootstrapping. So for example, an absolute loader, I haven't tried toggling these in to verify what they do, but they basically will start a small bootstrap routine by reading a bit of information from a device like a paper tape or a floppy drive, load that into memory, start executing it, and that will be a more complex loader that will read more information in from the device, put that into memory, and then execute that, and that will be an even more complex loader. And so we sort of bootstrap our way up to where we're pulling in maybe an entire operating system. That was a really fast, hectic overview of the instruction set architecture, but we'll talk about floating point another time too. Pull down a copy of the programming card, pull down a copy of that PDP 1170 handbook, or just search around online, find versions of this that suit you. Make your own excerpted PDF if you like, and we will jump into doing some programming in mostly in assembly language. We won't really get down to the machine language version a lot, but like I say, it's useful to know, for example, that a move instruction, I can use any source, any destination that I want, and to understand a little bit about how that works. So we'll jump into looking at the assembler and then doing some assembly language programming in the next part of this this video series. All right, talk to you later. Thanks.